So good morning one and all. In this video we can discuss specific heat capacity of gases and that particular gases, monoatomic gases, diatomic gases and polyatomic gases. Okay, the specific heat capacity. So we know that specific heat capacity, the amount of heat is required to raise the temperature 1 degree Celsius for a certain amount of mole is called the specific heat capacity. So here we consider here the monoatomic gases. So in monoatomic gases, each atom of a monoatomic gas has only three translational degrees of freedom. Also it is called the modes of monoatomic system. So modes are directions. Okay, three translational degrees of freedom. So thus the average energy of a molecule at a temperature T at temperature capital T is that is 3/2 kBT. Okay, so this is the law of equipartition of energy is consist of kBT. 1 degree is consist of kBT. 3 degrees of freedom here, translational degrees of freedom here, 3 into half kBT equals to 3/2 kBT. So now here the total internal energy, total energy E, or it is also denoted U, of a mole of such a gas is U equals to 3/2 kBT into number of molecules Na, that equals to 3/2 kB. It is also written as kB into Na into T. kB into Na equals to capital R. So it is equals to 3/2 RT. Since here kB, Boltzmann's constant into Avogadro's number equals to universal gas constant. Okay, so internal energy U equals to 3/2 RT. Now the molar specific heat at constant value. So at constant value, so here delta V equals to 0, then delta Q equals to delta U. So we can, at a constant value, the molar specific heat Cv equals to delta Q by delta U delta T. So it is also written as delta Q equals delta U, then delta U by delta T. Okay, that equals to delta U equals to, delta U is nothing but d by dt of U equals to 3 by 2 R T. So here 3 by 2 is constant, R is constant, then T equals to 3 by 2 R is constant, d of T by dt. Okay, differentiation of temperature equals to is 1. So then Cv equals to 3 by 2 R. Okay, so we know that the ideal gas equation for an ideal gas equation, so written as Cp minus Cv equals to R. So here Cp equals to Cv plus R, that equals to, what is Cv? Cv equals to 3 by 2 R, 3 by 2 R plus R. Okay, now it is 5 by 2 R. So then the ratio of specific heats, the ratio of specific heats equals to gamma, it is denoted as gamma Cp by Cv, that equals to 5 by 2 R by 3 by 2 R. So then it is 5 by 3. So for monoatomic gases, the gamma value is 5 by 3. So here next, diatomic gases specific heat capacity. So here diatomic, already we are discussed about the diatomic shape. Diatomic shape is like a dumbbell. So examples are oxygen, hydrogen, nitrogen. So like that, these are the diatomic. So in diatomic molecules consist 5 degrees of freedom. So for the translational degrees of freedoms are 3 and rotational degrees of freedom are 2. So then 2 plus 3 equals to 5. So for rigid rotor, so it is a diatomic molecule treated as a rigid rotor like dumbbell has 5 degrees of freedom. Here 5 degrees of freedom. These are 3 translational, 2 rotational. So using law of equipartition of energy, the total energy of such a gas is the total energy, the total internal energy or total energy of a mole is equals to, so it is denoted as U equals to 5 by 2 kBT into Avogadro number. Okay, U equals to, so here 5 by 2 kB into Na into T. So Kb into Na equals to capital R. So it is also written as 5 by 2 R into T. Okay. So this is U equals to. So next here it is consist at constant volume. Okay. At constant volume. So Cv equals to 5 by 2 R and Cp equals to Cv plus R, that is 5 by 2 R plus R, that equals to 7 by 2 R. So for rigid diatomic rotor, gamma equals to the ratio of specific heat gamma equals to Cp by Cv, that equals to 7 by 5. Okay, gamma value is 7 by 5. Next we consider non-rigid rotor. Non-rigid rotor. So for non-rigid rotor, diatomic is also consists the vibrational mode. Okay, then the degrees of freedom, equals to 7. So that is 3 translational, 2 rotational and 2 vibrational. So then the total energy, the total internal energy U equals to 7 by 2 kBT into Na, that equals to 7 by 2 RT. Okay, now at constant volume the specific heat Cv equals to 7 by 2 R and Cp equals to 9 by 2 R. The ratio of specific heat, specific heats equals to gamma equals to 9 by 7. So this is about diatomic gases. Now polyatomic gases. The polyatomic gases is nothing but, so for example H2O, C2H6, CO2, CH4. So like the 3 or more atoms is consist a gas is called the polyatomic gases. In general, a polyatomic molecule has 3 translational, 3 rotational degrees of freedom and at least 1 or more number of vibrational modes is called the polyatomic gases. So according to according to the law of equipartition of energy. So total energy, the internal energy total energy U equals to, so 3 by 2 kBT, 3 translational 3 by 2 kBT plus 3 by 2 kBT, 3 rotational degrees of freedom plus F is the modes of vibrational, so kBT into Na. Okay, now that equals to 3 by 2 plus 3 by 2, 3 plus F into kBT into Na. Okay, here kBT into Na equals to R, 3 plus R into T. So this is U equals to, total energy equals to. Then the specific heat capacity of at constant value is taken as CV equals to, so this is 3 plus F into R, and specific heat at constant pressure Cp equals to Cv plus R, equals to Cp equals to 3 plus F R plus R. So then it is written as Cp equals to 4 plus F into R. Okay, so this is Cp and Cv. The ratio of specific heats gamma equals to Cp by Cv, that equals to 4 plus F divided by 3 plus F. So this is the equation for polyatomic molecule, polyatomic gases.